Hi folks, welcome to our next video. In this video, we're going to be taking our concept of orthogonal vectors and generalizing them to all inner product spaces. And then we're going to be saying, okay, so let's say I have a basis that's not an orthogonal basis. How can I use that to help me find one that is? Because it turns out, as we can see in theorem 18 here, orthogonal sets have some nice properties. So that's where we're going to begin. So if I have an orthogonal collection of vectors, then we have these three properties. First, if I were to take the norm of the sum of all of those vectors and square it, that would be the same as if I took the norm of each individual vector and squared them and then added those up together. So this is not a thing that is like typical, right? Like we can't distribute squareds and things. So this is a nice feature of orthogonal sets. Also, if I multiply those vectors in the set by any scalars, that's not zero, then that set is also orthogonal. This is going to be helpful if we want an orthonormal set as opposed to just an orthogonal set. So remember, an orthonormal set is any orthogonal set of vectors that has a norm of 1. So number 3 is telling us how we can find that orthonormal set. So if you take the vector and you multiply by the reciprocal of its norm, then you're going to normalize that vector so it has a norm of 1. And yeah, so then you'll have orthogonal vectors whose norms are all 1. And remember, we needed orthonormal columns in an orthogonal matrix. So orthonormal is going to help us when we talk about orthogonal matrices again in the future. So these are some nice properties. So, okay, what's a good method to find such a set? So this is what we've called our theorem 19, and this is called the Gram-Schmidt process. And it gives us sort of an algorithmic way of finding an orthogonal basis, which we can then turn into orthonormal if we so desire. So here we have an inner product space V, and its bases are going to be the VIs, and we're going to use F to represent orthogonal vectors. So we're going to use the VIs to help us create these orthogonal vectors. So to start out with, we're just going to say, you know what, the first vector is the first vector. So that's this F1 equaling V1, right? So our first vector in our orthogonal set is going to be the same as the first vector in our basis. This is really an arbitrary choice, but we have to start somewhere. So this is where we're going to start. Next, what we're going to do for our second orthogonal vector is we're going to take the second vector of our set and we're going to subtract off its projection onto that first vector we chose. Basically, what we're doing here is we're saying, I want my vectors to be orthogonal, which means I don't want, like if I'm a vector, I don't want any component of me to be able to be expressed as part of other vectors. I need to be like separate, distinct from them so that our inner product is 0. So what we're doing here is we're taking vector 2 and we're subtracting off the piece of that vector that lives on this first vector we've chosen. And then we're going to repeat this process until we get to the end. So for example, the third one, I'm going to take my third vector in my set. I'm going to subtract off the piece that lives on that first vector I've created. And then I'm going to subtract off the piece that lives on this second vector that I created. So that now these F's are going to be orthogonal because I'm taking off pieces that lived on them and just keeping the piece that's like unique, the piece that can't be written as a linear combination of the others. And then we're going to keep doing this until we get to the end. So this collection of vectors forms an orthogonal basis, and it's going to have the same span as the space that we had before, since it's a basis. So what we're going to do, we're going to use the Gram-Schmidt process to work through 2 examples in this video. These problems are a little bit longer, so you want to make sure you have plenty of space to work on, which means I'm probably going to have to be erasing a little bit on the board, but we will do our very best to do this. So I'm going to take a moment and write the problem on the board, and then we'll get to solving it. Alrighty, folks, so here's the problem that we're going to be doing first. So example 33 says, let's find an orthonormal basis for this subspace of R3. So V is equal to the collection of vectors who look like this, and we're going to use the inner product is the dot product. Now, to help us out, we are generalizing our formula for the projection to be the inner product of the two vectors, not necessarily the dot product. So on this example, we'll be using the dot product kind of as a warm-up. On the next example, we'll be looking at an example from M22. So we're not using the dot product there, we're using a different inner product, but this process will generalize. Make sure you take your time with this process, make sure your calculations are as precise as you can make them, double check your work, because one small mistake early on has a terrible trickle effect throughout the entire problem, okay? So just be forewarned with that, check your work often. So in order to find an orthonormal basis, we have to find a basis to begin with. So this is a review question. Pause the video here and find a basis for the set V. And then when you're done, unpause and I will show you the basis that I found. Don't just wait for me to show to you. Please pause the video and work through it. It's important to practice this concept. All right, so here's the basis that I found. So what I did was I took this vector. I have no relationship among rho, eta, or mu. So I just separated it out in terms of rho, eta, and mu. So rho only showed up in this top coordinate. So I have rho times 1, 0, 0. Eta showed up in these two. So we have 0, 1, 1. And mu showed up in all of them. So we ended up with -1, -1, and 1. So these were the three vectors that I found. I'm going to call them V1, V2, V3 for easy reference. And then because we want a basis, we have to check for independence. So don't skip that step. It's important to do because maybe one of these vectors is a duplicate of others. So for my independence check, I just found the determinant of the matrix whose columns are these three, making sure that it's not 0. It wasn't 0, it's 2, which means that they are linearly independent, which means these three vectors are going to form a basis for us. So in order to find our orthonormal basis, our first piece is to get a basis, which we have found, huzzah. So next, we're going to apply the Gram-Schmidt process to help us find an orthonormal basis. So I'm going to give myself some room here, and then we will start in on the Gram-Schmidt process. All right, so I've given myself a clean whiteboard to work on, but I've also summarized some important information off on the side here that's going to be really helpful as we work through this problem. I don't know what that noise was. So this first piece is from our Gram-Schmidt process. This is our definition of projections that we want to remember. And then these are the three vectors that I found for our basis. Now, because our basis had three vectors in it, we only have to go up to F3 for our orthogonal basis here using Gram-Schmidt. If our basis had 7 vectors in it, we'd have to go 7 layers deep. Okay, so it depends on how many elements are in your basis. So to start out with, our first vector for our orthogonal set is the same as the first vector in our set, in our basis. So I'm going to let F1 equal 1, 0, 0. Easy enough. So F1 equals 1, 0, 0. Well, now what I'm going to have a tendency to do just for myself as I work through, because I'm going to be referencing this in all the future pieces, right? So F1 gets referenced here, and it also gets referenced here. There are some pieces of it that I'm going to want to have available to me. In particular, I'm going to want the norm of F1 squared handy. So over here, I guess maybe on my scrap paper or something, I'm going to write down the norm of F1 squared. That's going to be the square root of 1 plus 0 plus 0 squared, which is 1. So what this means is anytime that I have F1 that I'm projecting onto, I know that the denominator is 1. So that's actually really nice in this case. So let's find F2. Let me use a different color for that. Let's try green. Let's see if green works today. F2. So F2 is going to be V2 minus the projection of V2 onto F1. So F2 is going to be V2, so 0, 1, 1, minus this projection. Now, if you want to write the formula in here, you can. I'm going to just jump directly onto this piece. Oh, yeah. So for this piece, we're using dot product. So I'm going to keep it dot product. So off on my side here, I guess what I'm going to do is I'm going to do the dot product of V2 with F1. So I'm going to do V2 dot F1 off on the side. So let's see, that's going to give me 0 plus 0, oh, plus 0. Oh, actually, this is beautiful because I get 0 over 1 times 0, 1, 1, which is just where I started with, 0, 1, 1. This is super nice. This does not happen often. Okay, so this is working in our favor here. All right, and then we'll do the third one. So for the third one, F3, we're going to take vector 3. So in this case, -1, -1, 1. And we're going to subtract off the projection of V3 onto F1. So to help me do that, I'm going to do V3 dot F1. So let's see, that's going to be not 0 this time. That's going to be a -1 plus 0 plus 0, which is -1. I'm also going to need the norm of F1, which I've already found. So that's 1. So I'm going to get -1 over 1 times F1. Oops. This should have been 1, 0, 0 up here. Sorry about that, folks. So we've got 1, 0, 0. Then we're going to do our projection of V3 onto F2. So we're going to subtract that. So I'm going to need to know two things. I need to know V3 dot F2. And I need to know the norm of F2 squared. So V3 dot F2. Okay, so here's my F2 and here's my V3. So that's going to give me 0, -1, plus 1. So is that giving me 0? Yeah, looks like it. So I don't have to find this, but I'm going to find it just for completeness' sake. So this is going to give me the square root of 0 plus 1 squared, which is 2. Okay, so this is going to give me 0 over 2 times F2, which is 0, 1, 1. So now simplifying this, this is going to be plus one of these. So I'm going to get -1, -1, 1, plus 1, 0, 0. So that's going to give me 0, -1, 1. All right, cool. So if all I needed to do was find an orthogonal basis, this would be it. So my orthogonal basis, I'll write it out over here, I guess. Is going to be 1, 0, 0, 0, 1, 1, and 0, -1, 1. All right, not too bad in this case. Got pretty nice for us. To check that this is orthogonal, remember our inner products have to all be 0. So I would find a dot product between each of these, make sure it's 0. So we have 0, 0, 0, good. 0, 0, 0, good. 0, -1, plus 1 is 0, good. So once again, if all we needed was an orthogonal basis, this would work fine. However, we don't want an orthogonal basis. We want to go the extra step and be orthonormal. So now we have to find the norm of each vector. And I know from up here that the norm of f is root 2. So the norm is not 1. So we're going to have to normalize these vectors. The norm of f1 is 1, right? Because 1 plus 0 gives me 1. Square root of 1 is 1. But this one, the norm of f2 is going to be root 2. And here, the norm of f3, oh my goodness, is also going to be root 2. Because if I have 0 plus 1 plus 1, I get 2 and square rooting that. So that's my root 2. So I'm going to have to multiply these two by the reciprocal of root 2 in order to normalize them. So I'm going to write my final answer up top and do my work below. So we already have our first vector 1, 0, 0. For this next one, I'm going to do 1 over root 2 times 0, 1, 1. But 1 over root 2 is the same as root 2 over 2. We want to have a rationalized denominator. Oops. Should just be ones. Skipped ahead here, because now when I multiply these, I get 0, root 2 over 2, root 2 over 2. And then the same thing for this third one, I'm going to get 1 over root 2 times 0, negative 1, 1. This is going to be root 2 over 2 times 0, negative 1, 1. So I'm going to end up with 0, negative root 2 over 2, root 2 over 2. And now if I were to find the norm of each of these vectors, it would equal 1. And still the dot product between any two is still going to be 0. So if you need to find an orthonormal basis, you take your basis, you have to find your basis to start with. Then you have to apply Gram-Schmidt to get an orthogonal basis. Then you have to normalize each of those vectors that you found. So the process can be quite lengthy. This particular example was probably the easiest form of this example, or one of the easiest ones, because we had relatively nice numbers to work with. Ones, we had plenty of zeros on our side. If we had something with like, I don't know, 7s and 4s and 3s and stuff, then it would just be probably much messier. So this was also using the dot product. So for our next example, we're going to do the Gram-Schmidt process, but we're not going to have vectors in R3. We're going to have vectors in M22. So give me a moment and I'll be back in half a second. All righty, our half a second is up and we have a new example on the board and a new basis for us to look at. So this is example 34. And it says we're going to transform our basis B into an orthogonal basis for M22. So we only need an orthogonal basis. Don't need to normalize our vectors at the end. Phew. And we're going to use the standard inner product on M22. Just a reminder, the standard inner product between two matrices is going to be the trace of A, B transpose. Right, so that's our it's going to be our standard basis or standard inner product. So we're going to apply our Gram-Schmidt process. However, because our basis has 4 elements in it, we're actually going to have to go to a 4th step. So the 4th step is going to be, we're going to take V4 minus the projection of V4 onto F1 minus the projection of V4 onto F2 minus the projection of V4 onto F3. So we have so much fun in this example. It's going to be great. So we're going to start out nice and easy. I'm going to label each of these and come up with our first F vector. So this is V1, V2, V3, and V4. And F1 is V1. So we're going to have F1 equals this vector here. 1, 1, 0, 0. Now, because we're going to need the norms of each of these, as soon as I finish finding each of the F's, I'm also going to find their norm to help me out. So the norm of F1 is going to be, well, we're squaring it, so I'm just going to do the norm squared. This is going to be the trace of F1 times F1 transposed. So this is going to be the trace of 1, 1, 0, 0 times 1, 0, 1, 0, 1, 0. So this is going to be the trace of, let's see, 1 and 1 makes 2, 0 and 0, 0, 0, 0, 0. So the trace of this matrix is the sum of the diagonal entries. So 2 plus 0 equals 2. Okay. Yeah. So let us give ourselves some space here. I'm just going to erase that. And just remember that this is 2. So I'm just trying to think of the best place to keep it. Let's put it over here. Okay. So the norm of F1 squared is 2. All right, so let's do the next one together. So we're going to find F2. And F2 is going to be V2, 1, 0, 1, 1, minus, and I'm going to write the formula out this time. It's going to be the inner product of F1 with V2 over the norm of F1 squared times F1. So let's find that inner product off on the side. And we already found the norm of F1 squared, so we're good there. So the norm, or the inner product of F1 and V2 is going to be the trace of F1 times V2 transposed. So this is going to be 1, 1 across the top, and then 0, 1 across the bottom. So this is going to be the trace of, let's see, 1 plus 0 is 1. 1 plus 1 makes 2. 0 and 0, 0 and 0. Okay, so our trace here is going to be 1. So this is going to become 1, 1, 0, 1 minus 1 over 2, 1, 1, 0, 0. So 1 minus a half is a half. 0 minus a half is negative 1/2. 1 minus 0 is 1. 1 minus 0 is 1. So this is going to be our other vector, F2. And because we're going to need it, let's find the norm of F2. So the norm of F2 squared is going to be the trace of 1/2 1 minus 1/2 1 times its transpose. So 1/2 minus 1/2 1, 1. So this is the trace. Oh, golly. Okay, so 1/4 plus 1/4 is 2/4, or 1/2. A half minus a half is 0. A half minus a half is 0. 1 plus 1 makes 2. So we're going to get 2 plus a half, which is 2.5 or 5 halves. Okay. So I'm going to ask you to pause here and find the next one on your own. So see if you can find F3. You're going to find F3 by doing V3 minus the projection of V3 onto F1 minus the projection of V3 onto F2. So the components that you're going to need to find, you're going to need to find V3 and the inner product of V3 and F1 and the inner product of V3 with F2. We've already found the norm of F1 squared, and we found the norm of F2 squared. So really the work's going to be in that inner product, those two inner products, and then finding the sum. So pause the video here, and when you unpause, I will have my answer on the board and we can check, make sure we're going along okay. All right, so how did we do at finding F3? Now let's find out. So I started out using our formula, right? So I took V3, which is the identity matrix. Then I have to subtract its projection onto F1 and subtract its projection onto F2. So I already had the norm of F1 and the norm of F2 over here. We found those earlier. So now I need to find the inner product of F1 and V3. So that's what I did over here, and I found a value of 1. This was actually really nice because the transpose of the identity is the identity, and if I multiply by the identity, it doesn't change. So really, I just had to find the trace of F1, and then ultimately the trace of F2, which was 3 halves. So I did 1 over 2 times F1, and then I have 3 halves over 5 halves. So here's my 3 halves over 5 halves times F2. Now the 3 halves over 5 halves simplified to 3/5, and over here I distributed the 1/2. I subtracted these two to get this matrix here, and then I distributed the 3/5 to get this one, and then I subtracted to get this matrix. So for my value for F3, I got 1/5, negative 1/5, negative 3/5, and 2/5. Then, because I know I'm going to need it in the next step, I just went ahead and found the norm of F3 squared. So I did that over here, and that ended up being 3/5 in the end. So if this is not what you got, you want to make sure you pause and kind of check your work. Let me get out of the way here. So pause, check your work, see if you made an error, or maybe if I made an error, and work out from there. Once you are satisfied with F3, guess what? We have one more to find. We got to find F4. So we're going to repeat this process using V4. So now V4 is going to, we're going to take, think of it as taking V4 minus the projection of V4 onto F1, the projection of V4 onto F2. And now also we have a third thing to subtract, the projection of V4 onto F3. So instead of 2 inner products, you're going to have to find 3. The inner product of V4 with F1, the inner product of V4 with F2, and now the inner product of V4 with our new F3. So we're going to do the same thing. Pause the video, work through it, see if you get the same answer. And I'm going to do the same thing, and then we will compare when we reconvene in just a moment. All right, so I've once again filled the board with some lovely math gibberish to find my solution. So let's see if what you got is the same as what I got. So I started out off on the side by finding the inner products of F1 and V4, F2 and V4, and F3 and V4. It was out of space, so I didn't write the full notation this time. So I found the product of the matrix times V4's transpose, but that was the same as V4. So that actually worked a little bit nicely, especially because V4 has all those zeros. So I got the first inner product was 1, the next one was a half, and then the third was a fifth. So I threw those in. So there's my 1, my 1/2, my 1/5. Then I threw them over the norms squared. So there's my 2, 5 halves, 3/5. Put the appropriate vectors in place. did some fun arithmetic with fractions, and ended up with my final F4 being 1/3, minus 1/3, 0, and minus 1/3. So when all is said and done, my 4 vectors that form my orthogonal basis are these 4. There we go. This would be my answer with a lot of work supporting it. And again, for this particular problem, the matrices we started out with had 1s as values. So we even had the identity, which made the trace really easy to find. So take your time with the arithmetic, work through it slowly if you need to. It's not a race. Double check your calculator's work because as you can tell, because each of these later things are based off of these earlier ones, you want to make sure you're taking it slowly because one mistake is going to have a nice long trickle down effect. So that's going to be it for this video. I think that's plenty enough exercise for our brains for the moment. So if you need to take a break before moving on to the next videos, please make sure you do that. In the next video, we're going to be talking about something called an orthogonal complement. Basically, it's everything that's in your set that is orthogonal, or everything that's in your vector space that's orthogonal to your set. So that's what we're going to be talking about next. And then we're going to be heading back into the land of matrices a little bit and eigenvalues and eigenvectors. So if you haven't looked at eigenvalues or eigenvectors in a while, you may want to refresh your memory on those because I'm going to be kind of going quickly through some of those steps. You want to make sure you're comfortable finding the characteristic polynomial and finding those eigenvalues. So take a break if you need to. And whenever it is, I will see you in the next video. Have a great one.